Hello friends, welcome to EC Academy. In this lecture, let us understand alternate CMOS inverters. Here, we'll understand the concept of Pseudo-nMOS inverters and Cascade Pseudo-nMOS inverters, which is very important in VLSI design and testing. First, let us understand Pseudo-nMOS inverter. This Pseudo-nMOS inverter is different than a typical CMOS inverter. In a standard CMOS inverter, you have both PMOS and NMOS working together. But in Pseudo-nMOS inverter, the PMOS, which is a pull-up transistor, has its gate permanently grounded, which will make PMOS partially on. So if we say PMOS is partially on, which means it is acting like a constant load, similar to how a depletion mode transistor works. This design is simple but has some disadvantages. Now let us understand the characteristics of Pseudo-nMOS inverter. Unlike a complementary CMOS inverter, which only uses power during switching, the Pseudo-nMOS inverter dissipates DC power whenever NMOS pull-down transistor is turned on. This is because PMOS is partially on and will be conducting little bit. Here the transfer characteristics of inverter depends upon beta n by beta p ratio. So this ratio affects both the output low voltage and switching threshold. So here you need to remember that unlike a complementary CMOS inverter, which only uses power during switching, the Pseudo-nMOS inverter dissipates DC power when NMOS is turned on. So this DC power dissipation is because PMOS is partially on and it is conducting little bit. So here the transfer characteristics of the inverter depends upon beta n by beta p ratio. So this ratio will affect both output low voltage and switching threshold. Now let us understand the DC transfer characteristics. So this figure shows the DC characteristics of a Pseudo-nMOS inverter. Here we have multiple curves for different beta p by beta n ratio. And also these curves will depend upon the device sizes. So here different shapes are shown to differentiate between different device sizes. As the size of the device varies, the output voltage will also decrease as shown in this second figure. So this characteristics helps us to understand how the inverter switches and maintains a signal level. Now let us understand the Cascade Pseudo-nMOS inverter. A Cascade Pseudo-nMOS inverter is shown in this figure. So here, as you can observe, two inverters are connected in cascade, or we can say two inverters are connected in series. This setup ensures the signal doesn't degrade as it passes through multiple stages. So to avoid signal degradation, the output of one inverter must be input to the next inverter. This will lead to a key condition, which is V out will be equal to V in, that will be equal to V inverse. Here V inverse is inverter threshold voltage. So for equal noise margin, we need to set V inverse to VDD by 2, which is 0.5 VDD. So at this point, the NMOS transistor will operate in saturation region with the condition V in minus VTN will be greater than 0 and less than VDSN. And the PMOS inverter operates in linear region with the condition VDSP should be greater than 0 and less than minus VTP. Now let us understand beta ratio calculation in Cascade Pseudo-nMOS inverter. The beta ratio beta n by beta p is very important in VLSI design. From MOSFET equations, for NMOS in saturation, we can say IDSN should be equal to 1 by 2 beta n V in minus VTN whole square. And for PMOS in linear mode, the current IDSP will be equal to beta P into VDD minus V inverse multiplied with V inverse. If we equate the current, we will get 1 by 2 beta n into V in minus VTN square will be equal to beta P into VDD minus V inverse into V inverse. So from the above equation, if we take beta n by beta P, we can write it as 2 into V inverse multiplied with VDD minus V inverse whole divided by V in minus VTN whole square. So for VDD is equal to 5 volt, V inverse will be equal to 0.5 VDD and VTN is equal to 0.2 VDD, that will be equal to 1. If we substitute in above formula, we will get beta n by beta p will be approximately equal to 3. So here we obtained the ratio 3:1 for beta n by beta p. A 4:1 ratio is preferred, but we can use 3:1 ratio for slightly lower noise immunity in VLSI design. Now let us understand the effect of cascading. If the beta n by beta p ratio is very small, the signal level will degrade. That will lead to unreliable logic transitions. If beta n by beta p ratio is high, this will ensure fast switching and better signal integrity. A proper beta ratio balances sharp logic transitions with less power dissipation. Now let us understand the applications of Cascade Pseudo-nMOS Inverters. These inverters are used in pre-charge logic circuits. They are used in memory cell design like ROM and PLAs. They are used in high density NMOS dominated logic circuits. Now let us understand CMOS Tri-State Inverter. A CMOS Tri-State Inverter is shown in this figure. So along with logic high and low, it is having one more state which is known as impedance state. That's why it is known as Tri-State Inverter. So this inverter introduces a control mechanism with a control signal CL. So CL bar is complement of CL. So here the control signal is given by CL. By introducing the control signal CL, the output will be logic high, logic low, or it will be in high impedance state. Now, when CL is equal to 0, CL bar will be equal to 1. The output is in a high impedance state, which is not driven by input A. When CL is equal to 1, CL bar will be equal to 0. The output will follow the input, acting like a regular inverter. Due to this additional mechanism, the tri-state inverter is about half the speed of standard CMOS inverter due to additional control mechanism. So looking at the applications, these tri-state inverters are widely used in clogged logic circuits. They are used in latches and multiplexers, and they are used in I/O structures. So finally, looking at the summary, the pseudo-nMOS inverters offers high transistor density and simple design, but it dissipates power. So they are commonly used in ROM and PLAs where they are used as memory. The Cascade Pseudo-nMOS Inverter improves the logic transition and it has a compact design, but it requires careful beta ratio selection. And these inverters are used in pre-logic and memory cells. CMOS Tri-State Inverter enables bus sharing, support clocked logic, but they are slower than standard inverters. These are used in latches, multiplexers, and I/O structures. So, the three types of inverters which we discussed are essential in low power, high density digital circuits where there is a trade off between power consumption, speed, and complexity of the circuit design. This is about alternate CMOS inverters. Hope you have understood the topic. Thank you.